Hey guys, welcome back to chapter 12. In this video, we are going to take our ability to determine if a reaction is spontaneous or not and apply it to something called Gibbs free energy. So the entropy of the universe, we said, is always increasing. So spontaneously, the universe is always getting messier. The problem is it's very, very difficult to determine if a chemical reaction is aiding in the universe getting messier or if it's taking away from the universe getting messier. It's really impossible to determine directly what's happening to the universe if all we have is a little teeny tiny chemical reaction. So if we want to be able to determine if a reaction is spontaneous or not, if it is aiding in the messy random dispersion of the universe, we can use something called Gibbs free energy. Okay. So Gibbs free energy is a state function that relates entropy and enthalpy of a given reaction. Okay. So it's convenient to have this thermodynamic function and help us, because it helps us to predict or focus on our system to predict if it's spontaneous or not. So we will define this Gibbs free energy in just a moment, but whether it's positive or negative will help us to determine if it is a spontaneous reaction or if it is a non-spontaneous reaction. Okay. Notice that the spontaneity of a reaction does have two factors, so it's kind of like a weighted balance here. So enthalpy certainly is a factor, but entropy is a factor as well. So both of those are going to help us decide if something is spontaneous or not. So what is Gibbs free energy? Gibbs free energy is the energy available to do useful work. So if Gibbs free energy is released into wherever the surroundings, that means that we have energy available to do useful work on something else. If Gibbs free energy is, if it's having to take on extra energy, then we wouldn't have any available energy to do work. We'd actually need to have an input of energy for that to take place. So we're starting to get to see the connection between spontaneity and Gibbs free energy here. Okay. We can think of Gibbs free energy, so it's going to help us determine if a process is spontaneous or not. A good way to think of Gibbs free energy is as potential energy of the state. Right? So if Gibbs free energy is a positive value, that means there is going to be energy that has to be put in to that system. If Gibbs free energy is a negative value, that means the potential energy is going down, right? And energy is just going to be coming off of that system. So if you think of Gibbs free energy as potential energy, then you can use this sign to think I'm adding, increasing energy, or I'm decreasing energy. Energy is being released. Okay. So here's the sign indicator of Gibbs free energy. So if Gibbs free energy is less than 0 or it's a negative value, that will tell us that is a spontaneous reaction in the forward direction. So if Gibbs free energy is a negative value, so less than 0, we can think about that as the energy is being lowered, right? And as it's being lowered, that energy is being released to do useful work. So we went from a place of high to a place of low energy. If Gibbs free energy is a greater than 0, so above 0, it's a non-spontaneous reaction. So if the change in Gibbs free energy is positive, that means we have to put energy into the system to make that happen. So we have to have an input of energy for that reaction to take place. So this would be like going from low to high. So think about walking that bike up the hill. There's an input of energy that has to happen. If Gibbs free energy, so we talked about positive, we talked about negative. If it is exactly at 0, then that system is at equilibrium. So we won't really talk about that at 0 in this chapter, but just know that it does exist. If there's a positive and a negative that exists, we have to talk about what it looks like at 0. What's free about Gibbs free energy, right? So what is it free to do? So the free energy is the maximum amount of energy released from a system available to do useful work to its surroundings. So what kind of work would we want to do to our surroundings? Maybe we want to move that car. Maybe we want to fly a jet. Maybe we want to power a boat. I don't know, something like that, right? So the amount of energy that's free that gets released from these chemical reactions is energy that can be put into some other process happening. So why isn't all of the energy free? Why don't we get back everything? What's free about the free energy? Well, the energy that is not free gets used up in other processes. So during a chemical reaction, some of the energy would go to maybe increasing the entropy. So maybe the surroundings get a little bit more organized, or the structure gets a little bit more rigid. We have less particles as the product. So sometimes we can, quote unquote, lose some of this free energy by making our surroundings more organized. This one's a little bit easier to think about. We can also lose some of that free energy to heating up the surroundings. So we don't mean to lose heat to our surroundings, but sometimes it happens. Sometimes things heat up and that energy is lost to something else. So Gibbs free energy is very analogous to chemical potential energy. And chemical potential energy we can think of as analogous to like storing mechanical energy, right? So we can use Gibbs free energy to help us measure like how efficient is our process. So if we were measuring how efficient is like a car engine, it's 30% efficient. That means 70% of that chemical reaction, the gasoline getting used to power our car, 70% of that is lost to other things. Heating up our engine. Our engines get really, really hot during that process. Maybe changing the entropy to something like from a gas to a liquid, so making it more organized. So car engines aren't terribly efficient, right? And if we were to do the Gibbs free energy calculation for that, we would see that it would be about 30% free energy gets released. Something like a fuel cell is much more efficient, so that's 80% efficient. So we wouldn't lose nearly as much of our energy to enthalpy loss. We wouldn't lose near as much of our energy to entropy loss. 80% of what we put in, we get out. So much more efficient. So think of it as kind of like storing mechanical energy, but instead of storing that energy for mechanical purposes, we're storing that energy for like potential energy purposes. We can fuel something else with that energy. Okay. In the coming videos, we are going to calculate Gibbs free energy. So we're going to look at a chemical reaction. We'll look at the enthalpy, we'll look at the entropy, and we'll be able to calculate Gibbs free energy, and then look at whether that value is positive or negative to determine if it's spontaneous or not. I hope you guys found this helpful.